We're Group 3 presenting the ASL Motion to Text Projection Project. In our group, we have Keone Adams, Lenz Congolo, Miguel Cordero, and Olamjide Coyote. Overview of our project, we want to design a glove that can translate live American Sign Language alphabetical gestures to the alphabetical text. We want to accomplish this using various sensors, including flex sensors, force sensors, accelerometer, gyroscope, and then machine learning software. For the output, we'll be using a light projector, which we'll be also designing to output the finalized predicted letter. Motivation behind this is we want to create a bridge between communication between the deaf community. We wanted to create a device that can also be used mainly as a teaching device, as a travel teaching device. Anywhere you go, you can teach American Sign Language. We also wanted to create awareness of ASL and generate a desire for more to learn and show involvement in the deaf community. Goals and objectives, we wanted to design the glove so that it can do 26 total alphabetical letters from ASL gestures conversion. The translation will be done through machine learning prediction algorithms, and we hope to accomplish this with high accuracy. We want to use a wireless power source and a wireless connectivity. We hope to accomplish this with a rechargeable battery and Bluetooth connectivity. We want energy efficiency across the board in both the glove and the light projector, as we would like the project to be overall energy efficient. We did reference similar projects from the past. One will be the Babel glove done at UCF itself, the other one being the sign language glove completed at Cornell University. The purpose of that was we wanted to reference something which we can have a starting point, also learn from any constraints that they had, and build on their projects, yet while still keeping it different and kind of still working as learning it everything on our own.
Alright, for project constraints, we had different types of constraints, but the one we faced was the economical and environmental constraints, mainly because of the global pandemic. Parts of the supplies we needed, we couldn't find in time, especially when we were designing our integrated circuit for the power source. We couldn't find the parts we needed. And the others are the safety constraint and time and educational constraints. For our general specifications, we wanted to achieve at least 3 general specifications. One being the electrical components. The electrical components must fit on the glove perfectly without falling off. The other one is the input data. We're trying to make sure that every single sensors we use, we're able to create input data, because we're going to use the input data for the machine learning to predict the letters. And for the letters, we were trying to make sure that we could predict all 26 alphabetical letters. For the engineering specification, we had 4 specifications in mind for us to complete. The first one was for the force sensor to significantly change the output when pressed. For Bluetooth connectivity, since we wanted a form of wireless communication, we decided to go with the Bluetooth connectivity, and then we're trying to make sure that we had a successful connection between the PCB and the PC, and to ensure that data was being sent. For the projection distance, trying to make sure that we had a 3 to 8 feet projection distance between the projector and the screen. For the flex sensor, we're trying to make sure that we had the bend resistance range of 45 to 125 kilo ohms, represented by changing output voltage of 3 to 5 volts, which is what we're going to use for our data set. For the electrical component and hardware design, we have our hardware block diagram, as you can see on the screen. We have our sensors connected to the MCU, and the MCU is placed on the glove. And then whenever we make our gesture, the data is being sent from the MCU to the Bluetooth via the Bluetooth module to the PC, and then we collect our data sets, and then we do our machine learning, and then the projector displays the letters, which is our output. So for finger bending detection, since our sign language gestures rely on fingers being bent, we needed a technology that could distinguish the bend angles, which you're going to see in the next slide. We considered different types of technologies, but we decided to go with the flex sensor because it was reliable, and it's been used in different projects, and it worked for them, so we decided to go with that. For the flex sensor, the flex sensors will be able to determine the bending of fingers, like I said earlier. We ensured we needed 5 for 5 fingers, and when there's a bend, we get the change in output on the voltage. Like I said earlier, again, we're going to use that to predict our data, predict the letter. From the comparison table, you can see that we decided to go with the Spectra symbol flex sensor, mainly because it was cheap, it was lightweight. There are two sizes, short and the long. So for people with short ends or long ends, you can choose what sensor you wanted. And from the design, the simple design, no coating on the components. Um, and you can see from the earlier slide, the flex sensor could predict at a nominal resistance could predict values, and 45 degrees bend could predict value, and a 90-degree bend could predict the values too. So you could actually distinguish between what values you're getting. And we would have gone with the bend lab flex sensor, but it's quite expensive, so we decided not to go with that. As you can see from the design, it's weather and water resistant. For the touch detection, we needed to implement touch detection to create better data sets for our machine learning module. Um, we we researched three different technologies, but we decided to go with the force sensors. Sorry. Um, we needed a sensor to be thin, lightweight, flexible, and reliable, so we decided to go with the Interlink electronics force sensitive resistor because, like I said, it meets all the required specifications for the design. When pressure is applied, the force sensor will experience a change in resistance, resulting in a change in output voltage. And the force sensor will be placed in between the index finger and the middle finger, and when pressed upon, should be able to distinguish between the two main letters we were trying to get, which was the U and the V.
Moving on to the accelerometer and gyroscope. An accelerometer is a device that measures acceleration of motion and makes it possible to obtain information in the most accurate way. Gyroscope is a device that is used to stabilize movement to get accurate data. The main reason we choose this device is because it contains a 3-axis gyroscope and 3-axis accelerometer, which will create a 6 degree of freedom, which will help us to read the output data of the 6 sensor on the glove accurately. As we were looking for the accelerometer and gyroscope, we were more focused on the price and availability. The table shows that the DSOs models were priced at about $12 each, and the ADX model was priced at $25. We choose the cheaper one because when comparing the feature, the only major difference is that the more expensive one can sense up to 200 Gs of force, but we concluded it was not necessary since both can accomplish the same task, and the Spark Fun accelerometer and gyroscope has two quick connectors to allow us an easy connection and disconnection between our jumper cable to the PCB rather than soldering. This is the LSM6DSOX schematic that help us to connect to our PCB. It was easy to make the connection since we were able to look at which pin will map to our MCU. The MCU is one of the components that is vital to our project. According to Merriam-Webster dictionary, a MCU is an integrated circuit that contains a microprocessor along with a memory and associated circuit, and that controls some or all the function of an electronic device or system. It is a compressed microcomputer built to control the function of embedded system in products such as robot appliances, vehicle, or any product that read, store, measure, calculate, or display information. This table shows the four MCUs we're comparing for our project. It shows that both CC2s have Bluetooth capability, while the CC3 model has Wi-Fi capability, and the MSB 430 has no Bluetooth or Wi-Fi capability. For our project, we would have preferred to using CC2 SIR since it has Bluetooth. However, it was not available. So we went for the MSB since it has the capability to receive external companion like Bluetooth and Wi-Fi module. This is the MSB 430 FR6989 IPN, which has 80 pins. We use this MCU in development kit for previous UCF course, Embedded System Junior Design. The datasheet was readily available for us. For our project, we decided to use a lithium-ion battery as our power source because of the freedom it's going to provide to the glove. The glove needs a wireless design so that no cable or wire are disrupting the movement of the hand. The battery will hold a charge for at least 2 hours and it can be recharged whenever we run out of power. When looking for a power supply for the glove, we narrow down to these three options. As we are using a wearable device, we needed to use the lightest power supply as possible. Just looking at the picture alone, we can tell that the lithium ion is a way to go since it gives 3000 milliamp at 3.7 volts. With two batteries, they will give 6000 milliamps at 7.4 volts compared to the two others battery. This is our project schematic with a MC117 voltage regulator implemented in the schematic, which gives 3.3 and 5 volt as output to power all the component on the schematic. You can see there is a pin for the Bluetooth device, the Bluetooth module, the gyroscope and accelerometer, all connected to the MCU, and also the pin for all the 6 sensors that are connected to the MCU, and also the LED that will tell us the output. They will light up when we have any output from the sensors. So this is our PCB. First, we design a PC without a battery holder, as you can see on the left. And when we're trying it, we decided that it was more efficient if we build everything on the PCB with the battery holder on it, like you see on the right. So this is the PCB we're gonna go with for our final implementation, and you can see that we implemented all the pin header for all the sensor, the gyroscope and accelerometer, and also the pin for the Bluetooth module.
So wireless communication is a very important aspect of our project. We want the glove to communicate wirelessly with the PC that's doing the translation without any wires in between, just connected wirelessly. We wanted to do this also with the projector, but that is secondary. Our main wireless communication is between the glove and the PC. We mainly consider Wi-Fi, Bluetooth, and infrared communication. Here's a quick table that shows a lot of specifications of the three that we looked and compared with. We ended up choosing Bluetooth mainly because it had enough range for our project. It could connect to enough devices. Security was strong enough for the type of data we're sending over. We weren't sending over sensitive data. If any of these things were different, like distance and sensitive data, we would have gone with Wi-Fi. Infrared was a good starting point, but it wasn't well for our project. So the software design, basically the overview of our software is we'll be using machine learning that's getting data from a data set created from the glove. We'll be using a data split between training and testing on a 70 and 30 split. Basically first the training goes to the model to train the model on that data, and then we'll send over the testing data to actually see the performance of the model, and with the prediction the model throws out, we'll be able to see the accuracy that it's actually giving us. We had to look over the programming language we want to use. We considered Python, C, and Java. We ended up going with Python for the machine learning and for the user interface because it's easy to learn, has extensive library for machine learning, and it creates a single programming environment for our whole project. We did use C a little bit for the embedded software of the sensors, but besides that, it was all Python. So we did go with machine learning because we wanted the predictions to be real and not hard-coded. We used supervised learning because we provided input and output data. We considered a few classification algorithms, including random forest, naive Bayes, support vector machine, and neural networks. Our main goal was to have an algorithm that could do multi-class classification for 26 letters. Support vector machine ended up being what we chose. The way it works is it finds a hyperplane with which maximizes separation of the data points to their potential classes. What's great about this is that it has kernel functions, so we can help with the smoothing and efficiency of the class separation, and this was very useful to us, so we can get the best accuracy possible. The only problem with support vector was it natively does binary classification, but we very quickly found out there is a way to do multi-class. There's two ways. It's one-to-one and one-to-rest. One-to-one compares each class to each other. One-to-rest compares one to the rest all at once. We did heavily consider neural networks for the project, even though we decided against it. It could do very well and had high accuracy. We just felt like support vector machines was good enough for what we were looking for. For prediction computation, we're going to be running the software on the PC, so it'll be getting the data and doing the computation. We were going to try to do an app, but we all had different phones, but we all had in common that we all had a Windows PC, so we could all work with that. It was easy to debug, and it was very useful for us.
All right, my name is Kiani. I'm going over the projector design. So below is a simple ray diagram showing the light propagation through the optical system. We are using a 50 millimeter diameter lens with a 50 millimeter focal length to collimate the light through the system. The image formed from the LCD will be displaying the sign language translations from the glove that will be sent through two 3070 reflected to transmission beam splitters and mirrors to create 3 identical images with virtually identical brightness. That image will then go through 3 convex lenses that will project the magnified image onto a trifold screen. We aim to find a lens that had a focal length within 100 millimeters in order to maintain the small projector size. Since we are only displaying text and not fully colored images, it was decided not getting a super high quality lens was not completely necessary. We found an online Amazon store that sold a large variety of lab equipment for classroom usage, including cheap lenses, which is what we decided to go with. Below is a price comparison of our lens and a Thorlab lens. The lens that we purchased worked perfectly when testing with the light source while being smaller and spending a fraction of the price compared to bigger companies. All right, for our display, our main option was to use either an LCD or a DLP chip since we wanted to use our own backlight to ensure the image would be bright enough for the projection. We decided to go with an LCD panel since our electrical and computer engineers have more experience with LCDs. We found an LCD made for projectors on eBay for only $18, which first we were more confident in being able to connect to our Raspberry Pi. With a lot of time being wasted on trying to connect this LCD, we purchased the Geek LCD that comes with the driver board and an HDMI port for easy usage and connection. Even though this was pricier and much larger, time constraints led us with little options but to purchase something more foolproof. All right, the light source we decided on was a high-powered triple-up LED star. It has a maximum brightness of over 5,000 lumens, while most outdoor projectors requires at least 2,500 lumens. We purchased it for the LED supply website, which is very informative and provided everything we needed to be compatible with the LED, including the power supply we're using and the LED optics that are able to focus the unpolarized light. The power source we're using is this buck-puck LED driver that allowed us to customize the constant current and supplies just enough voltage to turn on our LED. This driver comes with a potentiometer that allows us to change the voltage, allowing us to manually change the brightness of our projector. The size and dimming capabilities is what made this driver especially attractive for our project in comparison to a very similar product, the Buck Block, which did not go in the potentiometer, is more than double the width. So for the screen, I got a cheap pack of acrylic sheets and a bundle of plastic hinges to create a clear standing trifold screen. The reasoning for making the screen clear is because of how much deaf people rely on body language and facial expressions. No matter where the glove wearer is standing behind the screen, viewers are able to see all forms of expression. We also found some cheap samples of self-adhesive projection film that fits perfectly onto the acrylic panels. Clear projection screens are not commonly used, so finding an affordable film was rather difficult. Our best bet was to purchase samples that were just big enough for our screen. This is a simple ray diagram of how the projector is going to work. And these are going to be the administrative details. And this is just a project budget list of everything that we spent on this project.
Here's the budget for the glove. We say we've been a pretty well budget. We spent a little bit under $300. The most expensive being like the flex sensors, just because we got so many of them. But since this was a self-funded project, we were very happy with this budget, and everything was at a decent price. The division of labor is pretty straightforward. For sensor testing, Jade and Lens took that equally, even though Jade headed that as a primary. Glove construction, we divided it between the three of us, but Miguel, took kind of the lead on that, and then Lens took the secondary. Software development, I took the lead on that, and then Jade helped me as a secondary. As far as electrical design, Lens did take the lead on our whole electrical design for our project, and Jade helped him as a secondary. For both projector component testing and projector construction, Keone took the lead on both of those. That was her main focus on the project, and then we helped her in every way we could with anything that has to do with software, electrical, or just the building and putting it together. Project progress, we're basically at 100 now. We agreed that we're like at 95, 98% because things like research and software development can always be improved and it can always be added to. But overall, we're happy with the design, hardware development, and testing. So we consider this a complete project. If you have any questions, please feel free to ask. We'll answer them to the best way we can, and we hope that you enjoyed our project and presentation. Thank you very much.